So today we're going to be talking about experiment 12, which is the bromine addition to an alkene. And this reaction is set up because there's actually two possible routes that one can conceive of for the addition of bromine across an alkene. And I'm just going to start off with simple cyclohexene. This isn't the alkene you're going to be using. We'll talk about that in a moment, but this just illustrates the point that I'm trying to get across. There's two mechanisms that one can imagine for the addition of bromine to an alkene. One is the anti-addition of bromine across the double bond to give the anti-addition, where you've got one bromine coming out of the plane towards you, one bromine going behind the plane of the board away from you. And of course, this would result in a racemic mixture because we have the RR stereocenter, so we could also have the enantiomer, which would have the SS stereocenter. Remember that if we start with a molecule that has no chiral centers, we must, in a reaction that generates chiral centers, get a racemic mixture, and that's in fact what would happen in this particular case. We can also envision a scenario where the alkene has the two bromines added in a syn fashion, that is on the same side. In this particular example, I've got these drawn out where the two bromines are coming out of the plane of the board at you. This results in a meso compound. Notice that it's an RS stereocenter, and so right through here we would have a mirror plane of symmetry, and so this is not a chiral molecule. It does not rotate plane polarized light, as each one of these enantiomers would rotate plane polarized light in equal but opposite directions, of course. The important thing about this scheme that I have drawn here is that this actually allows one to determine whether or not you have anti-addition of bromine or syn addition, because a meso compound and this racemic mixture are actually diastereomers with respect to one another. And so what does that mean? That means that we would expect this racemic mixture to have different boiling points, different melting points, would give different NMR spectra, for example, as opposed to the meso compound, which would have different physical properties. And so we can isolate the product that we get, or the products that we get, analyze them, and determine whether or not the mechanism of bromine addition is either syn or anti. So I want to quickly talk about how the mechanism goes for the quote-unquote anti-addition and the syn addition. And so in this particular case, we're just going to start off from our alkene. It's going to function as the Lewis base, and bromine is going to function as a Lewis acid. And so if we draw the bromine out, we've got this bromine-bromine bond, which is polarizable. And so electrons at any given moment can actually be closer to one bromine than the other and generate a partial positive charge on one of them. And so what happens is the electrons from the alkene react with the electrons on bromine, breaking that sigma bond between the two bromines. And we can also have the lone pair of electrons from bromine coming back and attacking what would appear to be a carbocation, if you will. This all happens in kind of a single step. And so what you end up with is a bromonium ion, where it's a three-membered ring. Bromine now has a formal positive charge. These are, as you can expect, not terribly stable. And so now bromine, or bromide I should say, comes in and attacks one of the carbons and breaks that weakened sigma bond between the carbon and the bromine. And this accounts for why we have anti-addition, because the bromide can only come in on the back side of this bond in an SN2-like fashion. And so that's why you end up with the anti-addition. However, one can also imagine a situation where the cycloalkene reacts in such a fashion where the alkene attacks the bromine, and immediately the bromine electrons from the sigma bond attack the other carbon, and that's how one could, in theory anyway, get to the meso compound. And so What we're going to be doing this week in lab is actually using transenamic acid to add bromine across, and there's a couple of reasons for that. Let me go ahead and draw that out for you. So we're going to be dealing with transenamic acid. It's a nice solid material. Cinnamic acid sounds like cinnamon, and actually it is one of the components of cinnamon. Cinnamaldehyde is what gives rise to cinnamic acid, which is a cinnamon natural product. And we're going to add bromine to this, and we're going to look and see what kind of products we get. So if we get the anti-addition, we're going to end up with this molecule plus its enantiomer. Okay. And this has a melting point somewhere around 203 degrees Celsius, so quite high. But if we go through the syn addition, we're going to generate an entirely different compound plus its enantiomer. And this one would have a melting point of around 93 degrees Celsius. There's a huge difference in melting point here that's easy to measure. And so what you're going to do this week in lab is you're going to take a methylene chloride solution of bromine, to which you're going to add your transenamic acid. Remember, bromine from the bromine test is going to be kind of a reddish color. You're going to be using 1 molar bromine solution, which is nice and red. And as the reaction proceeds, you're going to see that red color dissipate. However, if it goes completely colorless, you will need to add more bromine. We want to have bromine in excess to ensure that this reaction goes to completion and we convert all of our transenamic acid into our dibromide, whichever dibromide we have. And the only way to ensure that is by making sure we have adequate bromine. The nice thing about this particular reaction is transenamic acid is soluble in methylene chloride, but as the product forms, it actually precipitates out of methylene chloride. So the purification for this reaction is quite simple. You'll simply filter this, wash it to remove any excess bromine, and then you will thoroughly dry it. And it's very important to make sure that it is thoroughly dried before you go get the melting point, because recall from previous labs, if you have contaminants, that's going to depress your melting point and make it broader and make it more difficult to determine which one you have. So make sure your solid compound is dry before you load it into that melting point capillary and get your melting point. So good luck with it.